Okay, well, welcome to our second day of our introductory training on HPC performance analysis. The focus today is on profiling tools. The first tool will be presented by Cedric Valenci from University of Versailles, and it's going to be on MAQAO. So Cedric, I see your slides and you can get going.
Thank you, Brian. So good morning, everyone. So I will present our performance and analysis and optimization framework. So I will start with a general presentation on MAQAO, what it can do. And then I will switch to a demo. So first, briefly, how to launch MAQAO to analyze an application. And then I will spend more time detailing what kind of information we can find in a MAQAO report. So to start, this is a little exercise that we like to present because the question we may ask oneself is, do we really need to use optimization tools, analysis tools to find where we have issues in our code? So we could just think that we just need to look at the source code and get an idea of the performance issues and the bottlenecks. So this was an example of an actual code that we had to work on some time ago. And the idea is that looking at the source code and with some idea of the main issues of performance, we can find a few of them. For instance, there are indirect memory accesses. The number of iteration is variable, which can prevent the compiler from successfully performing some optimizations. There are also more indirect accesses. There are very expensive instructions. The loop itself is rather large. But the question is, if we see all of these issues, we want to know which is the most dominant one, and hopefully what could we hope to achieve in terms of performance gain if we manage to address some of them. And the idea is that this is simply not possible just looking at the source code. So for that, we need tools. That's something that Brian and Marta already covered yesterday. But anyway, so of course, we can have issues in different areas. They can be simply because the choice of matter of choosing the right algorithm, successfully implementing the algorithm, of course, making sure prioritization is correct. And sometimes also it's also a matter of correctly, successfully providing the necessary information from your compiler so that it can best optimize your code. And of course, there is this new issue that now systems are becoming more and more complex. In addition to parallelization, there are some specific instructions that have been added to the most recent processors, and we want to make sure that we are correctly using them. Which means that sometimes a code can have been successfully optimized for a generation of processors, but we have to restart the whole process once more for the next generation because it adds new instructions and that we want to make use of these instructions. So for that, well, the very first optimization tool is actually the compiler. And sometimes it's just a matter of being able to know which compiler flags we want to use, so that we can enforce some useful optimizations. Sometimes, of course, the optimization will require to be a bit more intrusive. We need, for instance, we may need to restructure the way we access data, change the structure of loops. And sometimes we may even need, some extreme case, we may need to change the binary code itself. Another point we really like to focus on is trying to identify which issues will be the most rewarding to fix first. Because if, let's say that we profile the application and identify that there is a section of code that is hogging 40% of the execution time, we say, okay, right, let's start with that. But if we had a way to predict that optimizing this particular issue will yield a 10% speedup, while at the same time a smaller section may yield more expected speedup, it will be interesting in that case to start with the second one first. And so this is the kind of issue that we keep in mind in our approach. So the idea is that the idea behind MAQAO is that we are trying to provide not only an analysis of the code, characterization of the code, how it behaves, what are the issues, but also trying to provide hints on how to achieve to address the performance issues that we have been detecting. So, as I said, it can be either just a matter of changing the compiler flags or having some idea of the type of code restructuring or data access restructuring that we want that we need to perform in order to improve the code performance. And really, we are really trying to guide the user in addition to provide just a set of metrics about the application. There is also a strong philosophy in MAQAO. We are working on the binary code itself. So the idea is that we're analyzing the compiled application, so that way we are able to assess what kind of transformations the compiler did or failed to do, for instance. And also if we need to, let's say, modify the code to insert some probes, then the binary code is much closer to what is being executed because it is what is executed. And so that way we avoid having some side effects by, for instance, modifying the source code to add some probes and causing the compiler to make different choices than without the probes. Also, the interest of working at binary level is that we are agnostic with regard to the source code language used, provided, of course, it is compiled. Because, yeah, if you are using interpreted language, it's not technically binary code. So that's why we say what you analyze is what you run at. So MAQAO has been in development at University of Versailles since a bit more than 20 years now. So historically, the very first version of MAQAO was actually focusing on Itanium code for those who may have heard of it. So we are focusing much more on obtaining performance at the core level or node level. So we are really trying to find how to make best use of the processor capabilities. That doesn't mean that MAQAO offers no insight with regard to parallelization, but really our core of expertise is really focusing on making sure we are making the best use of the processor capabilities. And in addition of that, we are also trying to provide, as I was saying, trying to provide hints to guide users really instead of just providing just a set of metric. And this is not only providing some hints on what to do, but also trying to provide information on the gain we could hope to have by addressing some issues so that we know where to start. So MAQAO is modular. This means that we can have different modules that we can add to the core of MAQAO as either from our side, we can develop new modules, and also we can choose to activate one or more of these modules during analysis. So MAQAO is working for x86 architecture and ARM architecture. So we are lacking a few features for ARM for now, but they are mainly concerned patching with it, which is not in the main binary release. We have some working prototypes for analyzing AMD GPU codes. And importantly, we provide MAQAO as a static executable. So it's available for download on our website, and it's possible to directly download it and run it right out of the box on any let's say, most Linux systems, which means that, you don't need to install it. So in addition to what I presented yesterday on how to actually use the MAQAO reports to identify some issues, here are a set of success stories on other applications that we had to analyze with MAQAO. And what I want to stress here is the type of issues which are a bit more complex than what I presented yesterday. And especially not only the type of issues, because in the POP3 assessment, we mainly reported the issues. And here in these cases, these are examples where we actually we had been working with the developers to address them. So there was the whole optimization process. So in this case, for instance, we identified that a function was invoked inside a loop with identical parameters that did not depend on the iterations of the loop. So invoking a function is actually quite expensive in terms of time, because the system needs to store all the context and restore it when exiting the function. So we just had to remove the function from the loop, and we had a very significant performance gain at the whole application level. In that case, we had some issues in the ways data structures were accessed. So basically, there was one unnecessary level of indirection. In that case, we identified that the compiler had not vectorized some loops. And our analysis showed that it was actually possible, because the compiler by default is conservative and will not try any optimization that poses a risk of breaking something in the application structure. So we could enforce, had some compiler directives to enforce that the compiler will vectorize these loops. And in that last case, for instance, we identified, I talked about expensive instructions earlier. So division is a very expensive instruction. It takes a lot of cycle to perform, and multiplication a lot less. So at some point, there was a division with the same value. So we just needed to replace it with multiplying by the reciprocal. So we just had one division, and the rest was multiplications. And also we had some very small loops with something like 1 to 3 iterations. And in that case, unrolling it, so just writing the body of the loop 2 or 3 times, meant the processor didn't need to be constantly performing loop controls to check whether it was inside, whether it had to stay inside the loop. And for small loops, this tends to be more expensive than the cost of the loop itself. So this is our current team. There are 6 or 7 of us. In fact, we have basically 2 or 3 people in our team who are actually really developing into MAQAO. And a few others are, the others are mainly either working on prototypes for new modules, or actually using MAQAO for new analysis, for analyzing some codes and providing some insights. So our website contains some, you can find everything on our website. Just let me show it. It should work. Normally you should be seeing our website now. So yeah, here, for instance, you can download the latest version of MAQAO. So we have a release planned for early July, so in less than a month now. And there are some additional documentation. So you have this reference sheet that provides in a nutshell, the instructions, the main instructions needed for launching MAQAO and analyzing it, and then some extensive tutorials describing how to launch MAQAO, how to read the reports, and the like. And of course, we have some additional publications, a list of all the publications around MAQAO. Let me switch back to my slides. So yeah, I will come back to that later. This is a repository of the various analyses that we performed. The idea is that MAQAO generates reports in static HTML formats. So we uploaded a lot of them to a server, so it's possible to directly view these reports online. And I will use one of these later to show how to navigate a MAQAO OneView report. And finally, there is this email address if you have any additional questions, bug reports, feature requests for MAQAO. So before going further, I will just briefly present a few notions. So they may be familiar to some of you. Basically, there are some important features of the recent processors that we tend to focus a lot on, because these are the best way to increase performance inside codes. So first is the principle of vectorization. So the idea is that instead of performing operations one element at a time, when you are, for instance, dealing with arrays, you will be, yeah, the figure was cropped here. I'm sorry. But the idea is that instead of using one element at a time, you will be processing multiple elements, so 2, 4, 8 elements at a time, for basically the same cost in terms of processor cycles. So the benefits are obvious. If you manage to vectorize a loop, you could technically improve its performance by a factor of 2, 4, or 8. So this is a very important feature of processor. It's not new, of course, because it was introduced in the Cray computer in 30 or 40 years ago, I think. But it's really something we focus on. And I put some emphasis on it because you will see a lot of references to it in the MAQAO reports. Another point to consider is the AFMA instructions. So these are present in more recent compiled processors, let's say latest 10 years, for instance. Basically, the idea is that for the cost of one instruction, you will be performing multiplication and addition, or it can be subtraction. But anyway, the idea is that we'll be performing 2 operations for the price of 1. And for that, we also try to detect whether the processor can support that and provide some hints on how to ensure that the compiler will generate a code that features a lot of these instructions, because the benefits are once again obvious. Another point is the cache. So the idea is that accessing data in memory is quite expensive. So the processors are equipped with a cache, which is basically a smaller memory where it can store recently accessed data. And the idea is that, I'm sorry. The idea is that when we retrieve some data from the cache, we don't just retrieve this data. We tend to retrieve a lot of data after that, what cache line. And so this is why it's quite useful to access arrays in a sequential manner, because let's say, for instance, you are accessing this particular element in an array here. Everything else will be stored, everything that follows will be stored in the cache. So subsequent accesses to the array will mean you will be accessing data that's already cached. And so you will have a huge boost in terms of memory access. Conversely, if you have indirect accesses or non-regular accesses, where, for instance, you are jumping inside your array left and right, then most likely data will never be accessed. The data that you will be accessing will most likely not be in the cache. So we will constantly be loading data in cache and flushing it to access the next data. And this is much less efficient. So this is also why you will see in MAQAO reports some information on the way you're accessing arrays, for instance. That's strange. I thought I had an additional slides on compiler, but let's go on. Anyway, so MAQAO. So as I said, MAQAO works is a modular tool. So we have a core that is performing essentially extracting instructions from the binary code, reconstructing some kind of internal representation. So we can identify where are the loops, where are the functions. One important point you will see in MAQAO reports, we identify loops with identifiers, because it is possible that a single loop in the source code can correspond to multiple loops in the binary code. For instance, if the compiler has performed some versioning or managed to vectorizing it, but needs some small loops to load the vectors and unload them. So this is why we have a unique identifier affected to loops, but we also can tie them to the original source code. Next, we have a profiling module that relies on sampling. So Brian presented yesterday what sampling is about. Next, we have the static analysis code that will be working on the binary code to assess what kind of transformations the compiler performed. And finally, OneView, which does not performs any analysis by itself, but is in charge of launching the application. So it would need information how to do that, invoke the various modules one after the other, and then aggregate the results and generate high-level reports on the application. So LPROF is using sampling. So Brian presented yesterday the pros and cons of sampling. The idea is that we have a very decent trade-off between precision and overhead. Basically, at worst, I'd say LPROF has a 5% overhead, and that's really being severe. So basically, yeah, there are basically no overhead. We don't need to recompile the application. And the way we built LPROF is that we don't also need a specific version of MAQAO for different versions of the parallel runtime. Next is CQA. So this is the code quality analyzer. The idea is that we'll be working, analyzing the binary code statically, and trying to identify the kind of, the type of instructions that were generated, the kind of transformation that the compiler performed, and provide some explanation of what happens in the loop. So we tend to focus a lot on loops because, in HPC code, most of the code is generally in loops. And also loops are usually the part of the code that is the most frequently executed anyway. So we tend to focus a lot on that and provide some hints and work around, be it at implementation level or just providing some useful compiler flags to use. And we are trying to write that in plain English so that it's understandable by hopefully anyone. So MAQAO CQA generates its reports in the forms of what we call what-if scenario. Basically, we try to estimate what the performance impact will be if a transformation was perfectly applied to the whole loops, for instance, the whole loop that we are analyzing. So for instance, let us suppose that everything was fully vectorized inside the loop. This is maybe not possible, but the idea is to provide an optimistic speedup of what would happen to performance if this optimization was applied. The idea is that if we see that only a very low speedup is easy possible to achieve with this transformation, then it means that it's probably not useful to try forcing the compiler to perform it, for instance. So we have these various levels. In that case, we'll suppose that no arithmetic computation, basically no address computation is performed inside the loop. So this means we can have no specific operation to do to access data stored in memory. Mostly, this means essentially suppressing indirect accesses. So this is an idea to what we can gain if we manage to access data more efficiently, if we manage to vectorize all floating point instructions or vectorize everything. I will show that a bit more in details when I will present the MAQAO reports. So just to briefly come back to our original example, what kind of information could MAQAO CQA detect in this loop example I showed? So basically, we could identify that there is data is not accessed regularly. We may identify indirect accesses. We can also detect that there are these expensive instructions that are being used. So the variable of number of iterations is not something we can detect easily from the source code, binary code, except in very specific cases. And we can also identify what in this loop has been successfully vectorized or not. And this is something that was simply not possible to do just looking at the source code, because it implies knowing that what the compiler will do. So last is OneView. So OneView does not perform an analysis on its own, but it allows to automatizing the analysis process. Because historically, basically, how did we perform analysis? Which were just running lprof on the application, detecting the hottest loops, and then ask CQA to analyze these loops. So OneView allows to automatize that. And also, it can aggregate all the results it obtained from lprof and CQA and some additional analysis, and provide high-level reports. So we can obtain some speed-up prediction at the whole application level. We have also a high-level summary where, once again, we are trying to provide insights on the application performance and characterization in plain human language. And then providing some hints and some additional insights on parallel efficiency in this mode. So OneView can be executed in multiple modes. The very first one is simply profiling the application and then performing static analysis on on the application code. That's the basic level of use of OneView that we could call OneView 1. The scalability mode will involve multiple runs of the application. The idea is that we'll be executing the application multiple times with different parallel configurations specified by the user, of course. So it can be, for instance, the basic example is running the application on 1, 2, 4, 8, 16, 32 threads, for instance, one after the other. We can also change the parallel configuration. What happens if we run on one node, two nodes, etc. And then OneView is able to perform all these runs and then presents results side by side and along with an estimation of the parallel efficiency. So this allows to have insights on how the application scales when we change its parallel configuration. Comparison mode is an extended case of that. I presented that one also yesterday. The idea is that we can take multiple runs from either from the same application with different data sets, for instance, or we can even use the application on different architecture, different computer system, different compilers, and present the results side by side. So this is a great way to compare the performance of compilers, for instance, or even architectures to see whether the code is more efficient on an architecture than another. Last but not least, the stability mode, which I also showed an example of yesterday. Essentially, it's a very simple mode. We are just executing the application a given number of times. By default, it's 31, but we can reduce that if the application is really long. And the idea is with completely identical parameters. And the idea is to assess the stability of the execution time of the application, just to make sure, for instance, later on, if you have found an optimization that brings a 5% speed up, that you are not simply hitting the margin of error of the execution time. So so launching OneView, the idea is that to launch OneView, you will need to provide every needed information for executing the application. So this means, for instance, providing the parameters, if you have some, to provide the MPI command to use it. If you are using a job script, you will need also to provide it and maybe to modify a bit the job script to add some specific keywords. The type of report you want, and you can also specify all of that. Yeah, there is a stray quote here. You can also provide store everything in a configuration file and just provide it to MAQAO. By default, we generate report in HTML format, and this is what I will show, but it's also possible to obtain them in text format, just in case you are just on the console and don't want to launch a browser, but just want to check something, or you want to script something to look for some informations in the results. And you can also generate some XLS spreadsheets results. And of course, yeah, like overall tool, you can have some help. So this is the basic presentation of MAQAO. Next, I will show how to launch it actually, and then most importantly, how to navigate the results. So I don't know, are there any questions at this point? Don't hesitate to interrupt me or ask them in the chat. I can see them. Yeah. So you should have access to the slides later on. The slides that follow in the slide decks present how to navigate the OneView report. I will not present them because I will simply switch to live demo. But if you read the slide afterwards, you will see a summary of what I'm about to present. So very briefly, let's just say, I don't know, maybe I'm a bit too, maybe this is too small. Let me switch to something more. Just showing in a live example how you launch MAQAO. Let's just say that your application. So I'm just using a NAS benchmark. Let's just say here, for instance, that your application requires OpenMP, OpenThread, MPI run. Yeah, so this is just launching the application, and for some reason, yeah, so you don't need me to show you how to launch the NAS. The idea is that if I want to analyze the application with MAQAO, I just need to provide OneView, the level of report I want. I will specify the command that for launching the MPI. So let me see, I have a question in the chat. You mentioned that MAQAO can be used across different binaries compilers. It is constrained to x86. Does it also support analyzing ARM architecture applications? Yes. So MAQAO supports ARCH64 architecture since yeah, for 5 years now. Yeah, we basically all of the analysis that we present can be also performed on ARM architectures now. At least for the Neoverse N1, N2, V1, V2 processors. Yeah, MAQAO can provide the same information. I think I have an example of NARM. It's too long. And yeah, basically, we just need to provide all the information necessary for launching the applications to OneView and the level of report we want. We have some additional flags that we can also provide. So first, the application generates a demo effect, so crashes because I just tested it 5 minutes ago. And I think I know what's going on. No, still not. Okay, never mind.
You have M run instead of MPI run?
What did I write? Oh, yeah, thanks. Okay, so first we are profiling the application. So OneView explains what is been doing. Yeah, the application I use is taking 10 seconds, so this should be very very short. So yeah, we have some warning here, for instance, by default on some security level on the system. Yeah, especially here I'm using WSL in Windows, but sorry, let me check a question in the chat. Yeah, thank you. Yeah, so basically we're displaying this warning because there are some security features that can restrict access to the kernel information. But yeah, most of the time, basically, we can still provide meaningful information on the application. The only things we won't be able to provide is information of the about if this kernel paranoid is set to a higher level, we simply will lack information of what happens in kernel space. So most of the time you won't need that, except if your code is doing a lot of kernel access. But by default, you can have all the information you need on your application. And I don't know why it is taking some time. Yeah. So now the profiler completed, generated the results. Now we are performing the binary analysis on any loops and every loops and functions inside the application. Yeah, it's a bit slow because I think that my laptop doesn't quite like that Zoom is running at the same time. We are analyzing next the loops, the functions, and then we generate the reports. So you will see, yeah, report generation. And the report is here at this point. So it's a set of HTML files that we can directly open in the browser. So I will just show this example, and then next after that, I will switch to some examples that we have on our server that contains some more additional examples of reports. And where did the file open? No, it's not here again. Oh, well, Timo effects once again. Just leave me 1 second, please. So by default, the reports we generate the reports in a directory that contains a timestamp. It's also, of course, possible to provide a name to the experiment directory. It's also possible to reuse an existing experiment directory to add additional information or generate different reports. So this is the main view of MAQAO report. So what do we have here? First, one important piece of information, whenever there are these questions mark here, means there is some contextual help on what this tab is about. And also, normally, if you browse over any underlined information, you have a small tooltip describing exactly what the metric is about. Finally, when you have this little blue bar appearing on the left side of a metric, it means that if you click it, then you will display a graph on the right-hand side, and you can go back to the original graph with this return icon. So this first tab presents a set of global metrics. I presented already briefly this yesterday. The idea is that in this tab, can you all see my mouse cursor? Because I'm doing a lot of... So the idea is that here we are presenting, we are showing a set of metrics, so just basic metrics that we measure during the application execution. Total execution time of the longest thread. So the as I showed yesterday, we are expecting in a parallel code to have all threads have the same execution time, if or at least the longest being as long as the application. When you have a significant difference here, it can already mean that there is something seriously wrong with the application. The active time is essentially the average execution time, the actual average time during which the processor is actually working on the application. So this is, for instance, this will exclude time where the processor is not working on the application because of, for instance, I don't know, it's accessing I/O, or there is spending time accessing memory, or there is a sleep inside the code and the like, or load imbalance, or what have you. So this is the time, this is the ratio. So basically those are the same metrics, but we just want to have an idea of percentage of time where we're actually working. And this is the same metric, but applied to the number of threads. The idea is that we ask, for instance, for 16 threads, we want to have an estimation of the average number of threads that actually were active during so this is an average, of course, during the execution of the application. So the corresponding graph here, so the dotted gray line shows the number of launched threads, because, for instance, you may have, let's say, an initialization section, and at this point, you will have just possibly one thread active, so if you have a sequential section. And the red bars are the added activity of the threads. So on the whole, how many, which is the percentage of the threads that are active during this time? Let me see this other example here that I have, I think. Yeah, for instance, here, this is an example that's from our website, from the datafront.macao.org, where you have example of, this is a public site, you can access it. And for instance, this was an example where we had multiple sections, for instance, and you can see them here. You can see the number of launched threads that varies, and the number of active threads that also vary during the course of the execution of the application. So this graph is rather useful to have when you are when you just want to have an idea of the way the application behaves with regard to thread activity. This also, you may have noticed that in addition to running typos in my command line, I did not provide any information on how to, on the affinity of the code, how to pin the codes, codes to a given core. And this means that this affinity stability measures whether the processes are staying, the threads are staying on the same core or running around. And this is usually, you don't want your code to be running around, because the system will be running some switching of context to compile, to change the move across the cores. And this measures basically the longest time given the longest time the threads has stayed on the same core. Here we are 50%. This is actually really bad, because this means that the thread never stayed more than half the time of the execution time of the application on the same core. Here, as I said, we are focusing a lot of on loops. So we are providing the percentage of time in the code spent in analyzed loops. This is mostly to have an idea of the impact on performance we can have by focusing on loops. And here we provide the categorization of the time spent in the application. I already showed that a bit yesterday. The idea is what we want to know whether we spend time in the code of the application itself, in the runtime, in some, we don't display everything here if possible, but we could also detect whether we are using, for instance, memory function like malloc and free, or whether we are using string manipulation like memset, string copy, etc., or specialized math functions. Let me show a more complex example here. For instance, here we can have a full list and spending time in the system, spending time in. I will show the detailed report later on. But anyway, here we also focus a lot on what the compiler did. And so we are trying to detect here whether some basic optimization options were provided to the compiler. So for instance, here we have the additional score, which is very low because we detected that it's a very basic compilation that I performed. And so there are no specialization flag, no optimization flag. So basically O2 or O3 or fast. And there are no architecture optimization flag because by default, if we don't provide an architecture specialization flag to a compiler, it will try to work conservatively and generate the code that can run on most of the architectures for this, most of the processors for this given architecture. So for instance, in the case of x86, I think that if you don't provide any architecture specialization flag, it will try to generate a code that could run on a Pentium 5, I think, by default, which that's a bit back. So we detect that we should, for instance, provide at least mArch equal native, which say just compile this to optimize in accordance to the system on which you are compiling. And here we are trying to assess the efficiency of array access, whether we're accessing them linearly or irregularly, for instance. So this is around the root score. So this means that we're accessing arrays rather regularly. Just switching back to this report. So this report is an example from our website. It was generated using additional options. So we have some additional options that can detect the energy used by during the full execution of the application. And we can also, with the add these additional flags, detect the memory traffic on the application level. So it's a global view of the, and I think we have some, no, we don't have these graphs here on the next page, on the total memory traffic at the application level. So the next, let me just check something. Yeah, okay. The next array presents some potential speedups. The idea is that here we'll have an estimation of the speedup we could achieve at the application level if a given optimization was performed. Once again, there are optimistic speedups, so it's not guaranteed that we can achieve them if we manage to apply this particular optimization. But the idea is to get an idea on whether these optimizations are interesting to pursue. Because if we can detect, because it's optimistic, so basically it means that if we detect no speedup at all, then most likely you will have no speedup at all trying to apply this optimization. So first here, we are detecting whether the code contains branches, essentially. So whether you have multiple paths in loops, essentially, whether there are if statements inside your loops. And if statements are very detrimental to optimization because most of the time the compiler will not be able to vectorize a loop that contains too many if statements. So this is an estimation of the speedup we could have if we manage to have absolutely zero if statements inside the loop. And of course here, for instance, here we can see the expected speedup is almost 10% or something, 1%. So 1%, yeah. So the color is green because it means we don't have anything to gain here. So yeah, the higher the speedup is, that means the worse the code is in that regard. And so this is why the colors switch to green to mostly red, which would, I don't know if it was a red example. Yeah, for instance, it's become orange when we have a potential speedup that's very high. That's like when we say about someone that they have a huge potential for improvement. That's usually not a nice thing to say. So here you have the additional graph that shows the number of loops containing a given number of paths and the additional coverage. So for instance, here we can see there are 29 loops containing only one path, so absolutely zero if statements, and they represent 40% of total coverage. So yeah, this means almost all of the loops have only one path. These two speedups, I presented them yesterday. Basically, they tried to estimate the time the speedup would have if we didn't spend any time in the runtime, and in addition of that, if we had perfect load balancing between all threads. And this we already knew we would get something here because as we saw, we are spending nearly 16% of time in the OpenMP runtime. So this is basically the speedup we could have if we got rid of that time spent here. And next are the various potential speedups for the various potential speedups for the various optimizations we could have inside loops. So for example, here, if we had no address computation, basically, if all floating point operation was vectorized, if everything was vectorized, and if we were only performing arithmetic operations, and each time we provide a speedup at the application level and the number of loops to have reach 80% of the speedup. The idea is to know whether there are only a couple of loops that present an issue, or if we have to take care of all of them. And there is the associated graph here that shows the loops in decreasing order of speedup. So basically, those ones will be those that provide the most speedup, and the curve is the cumulative speedup. And so each dot here represents a given loop. And if you double click on the dot, if you manage to catch it, yeah. We're opening a new report, which is the dedicated report for this given loop. So on the left mode, you can choose what's inside each panel. Here, by default, will present the source code of the loop. So, of course, for that, we will just require that the application has been compiled with -G, the flag that ensures that debug information are loaded inside the file. Basically, that's the one you will need if you want to run GDB, for instance, if you want to run a debugger. So that's the main constraint on MAQAO. We can run without that. We can perform any analysis with MAQAO without problem. The main issue is that we'll not be able to tie our information to the source code. And here on the rightmost panel, you have this CQA analysis report. So we are trying to present the various issues in plain English. So explaining that the loop is not vectorized, and we are not using the full vector length available on the system. And we're trying to explain why this may be. So for instance, it can be that we are accessing data in arrays, in 2D arrays in the wrong order, for instance, which means that we are jumping inside memory, and it's not possible for the compiler to vectorize in that point. And we also provide some additional flags that could help. We can also, so here, once again, we provide the actual flag that would allow to specialize the code with regard to the system on which it was executed. Here, for instance, here we're describing the issues. We are detecting here some expensive instructions. So for instance, here, they are all in the same source line. And yeah, apparently, this statement means that we are running these expensive instructions. So yeah, they are accessing part of the vector, and they are preventing that must be an aligned move. Yeah, we are not aligned, so we're providing some hints on how to ensure data is correctly aligned. We're providing also so here we can't know exactly the number of iterations of a loop, but if it's significantly high, we suggest to enroll that. And we don't need to do that by hand. There is a flag, which also we reported on the compilation option score here. If enroll loops, it's usually a good idea to have it by default. The compiler will try to unroll loops so that it has less iteration and less time spent trying to determine whether it must stay inside the loop or not. So I want the zoom over. Yeah. This was for the loop report. So this was of course, this last tab for those who are interested present what's under the hood of CQA. So here, if you are expert, you can look at the raw metrics generated by CQA and the machine model on which it relies to generate all these information. What sort of information you can have? You can also get you can also look at the assembly code of the loop and to which source line assembly line given loops a given instruction corresponds. You can see also the call chain, so which functions invoked this particular loop. And you have also the load distribution of the loop itself. So this is really how it fared across the various threads of the application. And some additional advanced metrics. So going back to the global tab, the bottom panel just presents some characteristics of the system on which the experiment was performed, which number of threads we observed, what the microarchitecture of the system is, and some specific information on that, and a summary of the configuration that we will provided. And you can add a full configuration of OneView, so this can be useful if you are using a more advanced information than what I provided. These are in a nutshell all the information you could provide on you could set for executing the application. You can specify environmental variable, the you should have the various parameters for executing the application. And that's it for this global tab. I will just show briefly, but by default, you can have an overview of not only, so you have this online help, and if you want to use a configuration file, it's possible to generate one that's already empty, but contains various commands explaining what each of the parameters available correspond to. And it's also possible to which one is it? Sorry, we have a set of specific templates. Okay, create config template. Okay. I don't use that one a lot, but we generate some you can generate some pre-filled templates that correspond to some for instance a given analysis. For instance, here, if you are so here it's a very raw file. There are no commands, but for instance, we will provide the necessary information that we need to fill if you have this kind of experiment. So this allows to just have a sample of the configuration file you will need to fill for OneView in the case of this experiment. So next, I will switch to the summary tab. The idea of this summary is to provide once again some human readable information on the application and on the specific experiment we run. So here in this tab, we're providing an assessment of the quality of the experiment itself, because we may simply detect that there is some issue in the way the experiment was launched, And we can say here right away, okay, we do another experiment because something is wrong, and you will not have any useful information from this experiment. For instance, we want the profile to be the application to be long enough. As Brian told you yesterday, when we are using sampling, too short execution will not yield significant results. So we are checking whether the profile is long enough, and yeah, basically you will have a warning here. So you can guess, as you can guess, the advices appear in green if everything is okay, and orange or red if something is wrong. So, for instance, we are checking that the debug information option is available because it won't stop MAQAO from running, but you will not have very useful information if you were told that the loop at binary address 0x44xxx1 has a vectorization issue, for instance. So here you saw this warning that I had that the event paranoid was at level 2. Basically, it means that some metrics on kernel will not be available. So we just display that. It's in a range because, hey, on a cluster, you may not have the option to change it, but sometimes there are some specific parameters to provide to enable them. So here, that's what we saw. We detected that basically the architecture specialization flag is not present. And this is a big red flag because it means the code is simply not at all optimized for the architecture you are running the code on. We are checking whether the optimization flags are present and whether, yeah, we're not using fast math. Once again, it's in orange because this can skew some results if your code is dependent on that. Basically, this means that with fast math, the compiler will be much more aggressive with regard to optimization, but will change the order of some operation, which can have an impact on floating point operation results. So here we are assessing the overall quality of the code, whether, for instance, we're spending enough time in loops, whether thread activity is good, we are correctly, everything is active as we saw earlier. We are spending nearly 99% of thread activity, so no issue there. Loop profile is not flat. This is not a quality issue by itself, but it means that if you have, for instance, a code, and we had to analyze one like that once, where you have 100 loops, each taking 1% of the time, then even if you manage to find the best loop to optimize, each optimization will at most bring a 1% speed up. So it will be long. So this is why it appears here. It means that, hey, if it's very flat, this means it will be a bit hard to optimize. And here, as we saw earlier, for instance, this orange panel, we saw that the affinity stability was low. So we detect here that, for instance, the processes were not being bound to specific codes. And yeah, we're checking also here whether we function are correctly balanced, whether we are using specific math libraries. And this last panel presents an overview of the hottest loops of the application and the various issues that we detected there, and with an associated penalty score. So the idea behind this score is to whether it will be complicated or not to fix. So the higher, the most complex it will be to fix. So sometimes it can be hard because a given issue is present a large number of times, and you just say, okay, if it's present, for instance, so if you are memory accesses, for instance, that are unoptimized, then it means that you will have to optimize each of them because most likely it's the data structure that has to be changed, and that can be very difficult depending on where else it's used in the code. And we're providing these two metrics. The vectorization ratio is the ratio of instructions that could be vectorized, that were actually vectorized against the number of instructions that could be vectorized. So here we are almost not vectorized at all. And here, for instance, and here, this is whether we're using the full available length of vector for this system. So here we are not vectorized anyway, so we are not using the full length. But for instance, if you have 512 bits vectors available, we'll detect, because sometimes the compiler can vectorize, but using only the 265 and 56 bits threads. So let me just check here whether we have this case. For instance, here in this example on our website, this loop was completely vectorized. So all instructions that could be vectorized were vectorized, but it only used half of the vector length available for the system. So we can also detect that. And once again, if we double click here on OneLoops, we'll open the corresponding security report. And here you say, for instance, that, yeah, your loop is vectorized, but you have 512 bits available on this architecture, but you are only basically filling your vectors only halfway through. So you will provide some hints on how to obtain that. For instance, here we can say, okay, use this compiler flag to force the compiler to use the 512 bits vectors. And yeah, so if you double click, okay. Next, the application tab will present some global metrics at the whole application level. So you will have here the categorization pie chart along with the detailed values. So for each thread, how the categorization, the code was categorized there. So this is useful to see whether there are some discrepancies here. For instance, was in MPI. So these threads are probably the MPI master thread, and the other are just the OpenMP children, for instance. This presents a breakdown of the hottest functions, the 10 hottest functions across the various threads. So once again, this graph can be useful to detect whether you have a specific discrepancy between the threads. Let me just check if we have an example. Yeah, here, for instance, in this example, you can see some significant differences between the various threads in terms of, yeah, for instance, that one doesn't spend any time, and the other must be you spending time here, which is waiting. So these ones are waiting for another thread. Yeah, so here you have the breakdown of the function and the various libraries that were used by the application with the associated percentage of time. Yeah. So once again, we can see, for instance, that the OpenMP loop, we spent 16% time in the OpenMP library. Just as an aside, this is a very recent feature, so it will not be available on the version of MAQAO that's available from our website, but it will be available in the version we are releasing in July, early July. So this function view, it's so basically this is a standard view of the results of profiling. So it's a profile of the various hottest functions in the application. One important point, when you have this little triangle here, it means that the function contains loops, and you can view them by clicking on the triangle or just clicking the plus sign here to expand the whole loop nest. You can display here, we have the number of threads on which this function was executed. So it can be useful to detect when some function, let me switch to the larger report. Here you can detect some discrepancy, for instance, on the various number of threads, and you have the wait. So here we're spending some time, but only some threads are waiting, for instance. Some threads. What else do we have? Yeah, you can display the compilation option like I showed yesterday. So you can have for each loops the various compilation options that were used for compiling this function. Sorry, not this loop, this function, because sometimes you can have some difference. That was in the example that I showed yesterday. And yeah, you have some additional metrics there. You can see to which categories it belong. And you can also filter the results to only display, for instance, the function from one particular library if you want to focus, for instance, on only the OpenMP functions. Or you could have a much more complex code, for instance. Let me see here. Yeah, not enough, but no, we are spending time in libc in this code, and we want to see which libc function are being invoked, because there are some. This is probably because of OpenMP. So what I showed the call chains for the loops, and you can also display them here by right-clicking on a given function. And yeah, you can see where a function was invoked from. This is what I showed also yesterday to see where a waiting time was triggered from. So here, for instance, this is actually some waiting time, and it is, and you can see, yeah, it's internal to OpenMP in that case, but yeah. Yeah, this is most of what we can see here. So once again, if you double click on one function, you will have the corresponding CQL report. It is similar to the report you had for loops, only this time it's at the function level. So whether the function was vectorized or not, etc. And yeah, so next tab is essentially the profiling report for loops this time. I will switch to the one from the website because yeah, it has much more. So here basically the same ID. You will have all the hottest loop in the application, the percentage of time we spent in them. Here, importantly, we have also this vectorization ratio and length views. So as I said, whether the loop is vectorized and whether we used the full vector length for this available on the system. Yeah, the color is red or blue, whether the loop is hot or cold. You have the level of the loop, whether it's innermost. So innermost loop means it doesn't have any child loop. It doesn't contain any further loop. And yeah, or in between or outermost means it does not contain inside any other loop. And you can have, for instance, here you can display the array access efficiency. So how well this loop is accessing data. And for instance, I don't know if you can see this appear, but you probably have warnings. Yeah, essentially having this here means that the most likely data is accessed is not accessed sequentially. So either you have a stride when accessing the arrays, or you are just accessing them indirectly, which means you are jumping inside the array. And you can see that whether we are. You have the type of stride of accesses inside the loop that are using a given stride. So for instance, those are using stride 1, those are using stride 0. That means they are simply they are constant accesses. Anyway, you are accessing most likely a constant, and you have 4 indirect accesses, for instance, here. So 4 of the memory accesses in the loop. This is something you can see from the assembly code, but that's a bit. But you can see the various. Essentially the various memory areas that are accessed and whether you are accessing them regularly or not. So you have the stride here. I can just, if you see on the tooltip, there is this stride that provides the whether you are using stride 1, not constant. That means where you are just using indirect access, or we should have a stride 1 somewhere. Yeah. Let me go back to the loop report. So once again, if I double click on the loop, I will display the secure report of that loop. And you can have also the call chains are also available here. You can also see the distributions across the various threads of that loop. Let me switch to the global report. For instance, here, yeah, for instance, here, you can see when there are some imbalance for this particular loop, and we have also the same type of information, of course, for functions. So we have a very, very long name because it's, well, it's C++. And this last panel, I don't know where I am. Yeah, last panel will present how the application was executed on the system. So first here, you can see how many processes, how many threads, on how many nodes. I will just switch to the larger reports because we just have one node here. But when you have multiple nodes, they will appear here. And also you can see how the threads were distributed among the core units, the computing units. So here, yeah, you have this graphical view, the various threads, and if you hover over one thread, you can see on which cores the thread was executed. So as we saw earlier, the affinity was not good. So this means you can see that a given thread was run on multiple different computing units during this execution. And let me check on the larger reports where we had 2 sockets. And yeah, that one, for instance, was much more, had a much better affinity. And you can see that each thread was running on one single processing unit. And you have also the text view, which is less nice to look at, but more useful to get info at a glance on what is going on. So here you have a breakdown for each computing unit, each processing unit, how many threads run on it with the associated percentage. So here we can see that absolutely nothing was pinned. And for instance, conversely, here we have this example where you can see that for each processing unit, one thread only run on that. And there is the reciprocal view, which is thread-centered. So for each thread on which processing unit the thread executed. Sorry, I'm having an issue with my Zoom overlay. Yeah, let me come back. Same here, we have the same view that each thread was running on a lot of different processing units. So this is the main view for, this is an overview of the type of information you can find in the standard MAQAO report. I will just show now additional type of reports that we have. Before that, I want to try what I have. Not a lot of time, but I will just have fun and try a little experiment because since we are complaining that the code was not correctly optimized, I will just recompile my application and add the corresponding flag to see whether something was changed. We just relaunch an experiment, and while it runs, I will be showing you additional reports. Let's see that. Yeah, I got here. Okay, so let me go back here. So this is on our website, on our so datafrom.macao.org. It's linked from the MAQAO website. Where it must be. Yeah, you have some previews of MAQAO that links you here. So here we have a specific set of representative samples, and you can also browse additional applications that we analyze and the corresponding reports. So let me just show you the scalability report. So the scalability report, as I explained, just shows, allows to run the application with varying number of threads and processes, varying parallel configuration. So here, for instance, for this application, so we can specify names for the various runs so that it's easier to find what happened. And we varied the number of threads, which must appear here. So here we had always 8 processes, but we vary the number of threads between the application, and you can see between the runs, and you can see, for instance, the results side by side. And there is this additional metric here, the scalability gap. Once again, it's present in terms of a potential speed up. So what speed up we could achieve if scalability was perfect. So we are expecting speed to increase by the number. This is a strong scalability. So when you increase the number of seeds, of course, you expect time to be divided by the same number of threads. And this is what we expect. So for instance, we have 24 threads instead of 1. We expect 24 speed up. And this is what we observed. And this is corresponding speed up if scalability was perfect. So as we can see, it's more or less quite good until 8. Run 3, that's 8. And then everything goes to heck after that. And we are completely losing scalability after that. So the rest of the metrics is basically the same. It's just that we can see them side by side. I will just show in the application tab here, we have addition. So we have categorization for all the various runs side by side, which can be a great way to detect, for instance, that one where it starts going badly. We're spending some time in the OpenMP runtime. And you have the scalability information. So have a view of the efficiency. So we can confirm that it breaks down after 8. And you can also hear this. So this is an overview of the number of functions that have a given parallel efficiency. The idea is that we're trying to assess parallel efficiency at the function level. And we can see that here we are detecting which functions have a bad parallel efficiency, for instance. So here we can see this function fare rather well because we have a good parallel efficiency. So here that one is an outlier because it's an OpenMP and it's very low time. So this is why we're having weird results. But anyway, for the hottest functions, we can see what happens to these functions. They are the one with the incorrect efficiency. Similarly, in that case, maybe we have multiple threads here. No. So here, all the graphs are the same. Only here you can see the parallel configuration for the different runs that we performed. It's essentially the same view, only it's applied for the various systems, the various runs. So this was, in a nutshell, what the scalability report can provide for as information. What else do I want to show you? The comparison mode, for instance. So essentially, it's the same view as a scalability, except in scalability, we'll just launch OneView with scalability and specify in your configuration file what type of information what parallel configuration you want. But comparison mode, you can either do that, so just specify MAQAO, run MAQAO, OneView with very different data set, for instance, but you can also have different OneView results and just compare them side by side. So here, for instance, we are comparing different compilers, AOCC, GCC, ICX, and presenting the results side by side. So see, for instance, right away, there is something wrong when we are compiling with ICX, for instance. Get it. And apart from that, we can also, this is something I showed yesterday, we can try to have a level of comparison between the functions for each function. So we have some issues sometimes because the name of the function can be impacted by the compiler, for instance. But you can see side by side the various functions. We were relying on source information for that. So for instance, did we manage? Yeah, we managed, for instance, to link these loops together, even though they have not the same ID, but we saw that they had the same source information. And so we can present them side by side so we can see the differences on how, for instance, each compiler fared. For example, strangely, AOCC managed to GCC managed to use and ICX managed to use a bit more of vector length. They have a slightly better vectorization capabilities on that loop than AOCC, for instance. It's also possible, for instance, to have this for architecture. We had these results here where we're comparing, for instance, the same code but running on Skylake. So Intel Skylake, AMD Zen, and ARM Graviton G3. And we can have the same type of comparison, but this time across architectures. Just let me show briefly. I'm reaching my 90 minutes. Just this is the type of stability report that I presented yesterday. So the idea is that we're just running the application multiple times and see how its execution time varies from one to the other. And let me show with my scroll, because yeah, you can scroll on the charts, bar charts. And this is the statistical representation. So the longest execution time, you can see the percentiles here are very close. You can also detect here where there are some discrepancy just at a glance. The various, the various percentage of given execution times. So I think this is mostly all in terms of case. I will just switch back to my attempt to improve performance. I don't know where is. Yeah, never mind. And which one is it? So that's, yeah, 10. Just let me check that. So that's the latest report I launched. So that I just want to check the results with changing simply the compilation flag. So here we can see from the start, execution time is much better. We were 110 seconds, now it's 36. Compilation score has significantly improved. We just complained that, yeah, we don't have 03, which is a bit strange because I thought it was there, but anyway. And we'll see that the loops this time should be, not much well vectorized. Let me just generate a comparison reports between those two experiments. What did I do wrong this time? What? Oh, because I used the erroneous report, I guess. Yeah, because I did not do the right reports. Sorry. This is the first experiment. And this is the latest one. What the heck? Oh, yeah. So I'm just comparing these two runs I made, and just live making comparison between those two with or without the right compilation flags, and you can see the difference in total time. For instance, you can see you can see here, for instance, that vectorization still improved because the speed up, if we manage to vectorize floating point operation, the potential speed up has decreased. So vectorization was improved just by changing one flag that was provided by MAQAO. And let me check what happens on the function. So here we are managing, you are comparing the various function. Let me check the loops. we should see the difference between each of the loops of the application. Yeah, vectorization, so did not improve for that one. But anyway, yeah, I'm not quite sure we have the right loops here. Yeah, this is I mean, this was just to very quickly show that with comparison module you can just see what happens between two runs and just get them side by side. And yeah, but I will stop now. But we could also try pinning to see whether this has an impact, for instance. Yeah, so this is it for the this global presentation of MAQAO. If you have any questions.
Thank you, Cedric. I'll stop the recording now.